Right, then I'm going to be talking to you about the Salkin-Johnson vacuum in 2+1 dimensions. This is a project I did together with Yaseman Yazdi at Imperial. So, okay, first of all, what is the SJ vacuum and why do we care? So the SJ vacuum is a proposed distinguished vacuum state on curved spacetimes. Which is important because generally on curved spacetimes you don't get as easy a vacuum state as you do sort of in flat spacetime, which obviously throws up some problems when you want to start quantizing in a GR setting as opposed to just an SR setting. And then specifically, why do I care in this case? Because there are quite a few of these sort of proposed vacuum states. So one of the open questions in quantum gravity is whether spacetime is fundamentally discrete or fundamentally continuous. And so it would be interesting to see where the differences between the two, how are we able to distinguish between them, sort of, if we look outside. And so in this case, we care about the SJ vacuum because it's one of it is a distinguished vacuum state that can be defined both on continuous manifolds and on discrete ones. And so it is sort of the perfect setting for us to compare the two. And specifically, we used causal set theory here, which I'll come back to why we chose that later. But we compared the behavior of that to the behavior of the continuous Minkowski function, because that's what we know the SJ vacuum should be limited to in flat spacetime. There is some previous work on this, but it was in 1+1 dimension and indicated generally good agreement between the two in sort of regions away from boundaries, though there was some discrepancy between sort of continuous functions and discrete functions at the boundaries, though at the time that was sort of mostly put down to infrared pathologies in 1+1. So we decided to take a look in 2+1 instead. Okay, so how's the SJ vacuum actually defined? So we start with the Pauli-Jordan operator, which is defined as usual, though it's noteworthy that it can be defined both in terms of the Wightman functions and in terms of the green functions, which is going to be important for us later. So because I delta is anti-symmetric in a bounded spacetime region, we can express it in terms of the positive and negative eigenfunctions. And so we construct the SJ Wightman function by restricting ourselves purely to the positive eigenspace of the Pauli-Jordan operator. Okay. So causal set theory, what is it and why do we care? It's in some sense, it can be seen as potentially the most sort of bare bones discrete model there is out there, because what it does is it takes Lorentzian manifolds and strips away essentially all structure except the causal relations between points. So what I mean precisely when I say that we've got a causal set that we've made to be like a specific spacetime is that we've distributed points randomly in that spacetime, calculated the causal relations between them using the metric, and then discarded essentially all other information, which is what we call sprinkling, and which is what you can see on the right here. That's a causal set sprinkled into a 1+1 causal diamond. Right. What's important is that in CST we've got a proper time estimator. In fact, we've got more than one, but we chose this one for a variety of reasons. And that means that we can use this proper time estimator and construct a Green's function using it, which means we've got a Green's function for causal sets, which means we'll be able to construct the SJ vacuum. Cool. So what exactly did we do? So we sprinkled, here I'm going to be talking about 5,000 points into a 2+1 causal diamond, and then calculated the SJ vacuum across the entire causal set, and then looked at points within the central region so as to avoid the boundary conditions. So specifically, we chose a causal diamond for the inner region as well, because they're sort of nice shapes if you want to avoid hanging edges of the causal set going sort of out of that. You can see on the left is the side view of the causal diamond, on the right is the top view. Right, okay, so what does this look like? So here I've got a plot for space-like points, space-like separated points of the SJ vacuum and the Minkowski function. So generally, it seems that there is fairly good agreement for space-like points. We can see that there's this sort of for sort of low separations, the points don't quite all curve up in the same way that the continuous function does. But in general, it seems that there is definitely some kind of match here. However, if we look at the time-like separated points, we get a slightly different picture. So the Minkowski vacuum, or the Minkowski-Whiteman function, of course, is 0 in this case, but we can see that the SJ vacuum seems to curve up for low tau. Okay, so why is this the case? Well, we had a couple of ideas what could be causing the discrepancies. So first of all, let me take a look at what the Whiteman function actually looks like for Minkowski space. So we can see immediately that we are integrating over an infinite range of k's, so wave numbers. But of course, we are both working in a finite bounded region, so the causal diamond, and we've got a discretization scale. And so really that means that we've got a maximum wavelength and a minimum wavelength. So we've got cutoffs in both directions. So the first thing we did was imply a cutoff at the top end and at the bottom end. So that changes our integral to look like this, where the minimum wavelength will be on the scale of will be on the discretization scale, and the maximum wavelength will be potentially something like 2 times the size of the causal diamond. Then the second thing we did is we realized, of course, we're working in discrete space, so really we shouldn't be integrating, we should be summing, because we will only have certain k's. The problem here is that if we're working in a sort of randomized setting, we don't have sort of clean steps in our sizes of k. Really what we have is sort of a whole variety of different k's, which are each of slightly different size. So we added a randomizing factor in our sum going up. Okay, what does this look like? So first of all, again, for the space-like separated points, when we impose a cutoff, we see that the Minkowski vacuum sort of starts spreading out at low separations in a very similar way to our Sorkin-Johnson vacuum, which is a good sign. But the tricky question was with the time-like separated points. So what does that look like? Okay, so we actually start getting a curve up for low tau here as well, which is a promising sign. However, we've also got this sort of fanning out into negative values that we don't see in the SJ vacuum, which brings us to our second comparison. So if we take a sum instead, we see that there's, again, very similar behavior for the space-like separated points to when we just imposed a cutoff. Probably slightly less oscillatory behavior around the low distance regions. And again, for the space-like separated points, it's very similar. We've not, this doesn't unfortunately get rid of the behavior here we see at the bottom. So what can we conclude from this? There are clearly differences between discrete and continuous spacetimes. We've been able to isolate the cause of some of the differences. However, there are still a couple there that we don't quite know how to resolve. And I think it would probably be quite interesting to see where they come from. Thank you.
Thank you very much, and finished on time. So if anyone wants to ask a question, we have a little bit more time to discuss. Maybe I can get the ball rolling though and ask you about, in the causal set calculation, have you looked at how changing the size of the set, like how many, if you add more points, does it change the behavior of the scatter that you're seeing in your results?
Yeah, so we've run simulations from essentially everywhere from 1,000 points, and we're still currently running simulations for 20,000 points. Okay. It seems that the plots look approximately the same, independent of the size. So there's some variation, especially if you go to very low densities, but the 5,000 points seem to be fairly representative of what we're seeing.
Interesting. So questions come in the Q&A. I think you can see it. Marian asks, so is the aim to isolate the differences, or should the theories match?
Well, so that's kind of a question we went with going in. So obviously there are going to be differences between discrete and continuous spacetimes. And so we didn't know going in whether or not they would match or not. Of course, if they don't match, that means that a whole lot of sort of modern quantum field theory needs to be reformulated on discrete spacetimes. And so if they don't match, it is kind of important to isolate where those differences come from. I hope that answers the question.
I think it's a question of looking to see what happens, right?
Yeah, exactly.
Can I ask you a final question about the boundary conditions that you mentioned? I don't know if you said exactly what they were.
Of course. So I'm not sure I mentioned boundary conditions per se, but so what we've been looking at here is sort of only a central region within the manifold we were considering, or the space we're considering, which is a full causal diamond. In 1+1 dimensions, it was found that sort of around the edge regions, the SJ vacuum stopped looking like flat Minkowski space, and it looked like there was a static mirror in the corner. And so initially what we wanted to do was just sort of avoid any potential boundary conditions we may be seeing, any boundary effects we were seeing having an effect on our results, and just look at the central regions.
Okay, I was curious to know what effect those boundaries had.